All right, last time we ended off right before we got to the good stuff. Make sure the audio is going good. Where we can actually write a program. We're going to be using Google Colab. Google Colab is just a website you go to and you can start programming in Python right there in your browser. It makes it really easy to just start programming. If you already have a Google account, Gmail or whatever, you just go and it's there, you'll have access to it. If you don't have a Google account, make one. If you have some moral issues or privacy concerns of a Google account, just make the Google account strictly for your Colab, and then you're all set. If you really don't like it, then that's when we can explore things like Anaconda, getting it on your computer. So there's a link right here, Google Colab. You click it, it might take you to like a welcome page the first time you get there. If it does, you can just be like, yeah, just new notebook or whatever. And you're going to see something that eventually looks just like this. Yours might not have a black background or whatever. It might have a white background. Doesn't matter. You'll see something like this. And Python's ready to go. If you do have your laptops with you, I suggest you follow along. Go to this website. So you go to this website, and it's ready to go. It's just waiting for you to start writing a program. And we're going to write the most basic program there is. I want to be very clear about something though. What we're about to write is a program. There's no ifs, ands, or buts about it. I'm not being silly when I say, oh, we're writing our first program. We are, assuming you haven't written one before. And this program we're about to write is the quintessential first program everyone always writes. It's called Hello World. And there's a reason for it being so simple. It's just a way to make sure everything's working properly. And in Python, so the point of Hello World is just to tell your computer to print Hello World. That's it. And in Python, to get it to do that, you type print, open parenthesis. We need the parentheses. There's some pop-up stuff you don't need to worry about. Hello World. You'll see the one there. You don't write that one. That's just like a line number counter. See, they just keep going. And it doesn't really matter what line it's on. But if you do something like this and you hit run, you will see it just printed it out. Done. That's a program. That's a program. Raise your hand if you were following along and you got it working. Raise your hand if you're following along and you'll have it working in just 5 seconds. Just give you a second. All right. And that's it. That's Hello World. There. You've written your first program, assuming you've never programmed before. This little play button is the run. If you want to get fancy, you can hit Control-Enter, and it'll run for you as well. And there we go. That's it. That's Hello World. What's really cool about Colab is it's this thing called like notebook-style programming, which is really great for things like course notes. Because you can write your programs here, but you could also add like additional blocks of programs, of code, so it's separated nicely. You can even add blocks of text. Be like, this was my first program. There, and now there's like text, so you could actually take notes there. I'm zoomed in a lot, right, so you can't, it's kind of hard to see. If I'm zoomed in at this level, how easy is it to see at the back? Still good? How about now? Yeah, but are we pushing it? I won't go worse than this. All right, you know what? Let's go there. So you can also add notes here. So it's great if you're following along and you're taking notes, and then you've got a program, and then you're taking notes, and then your program, and so on and so on and so on. It's great. And that's it. That's our first program. Done. Did anyone get stuck on this though? Because every year there's always a couple people that a couple funny little things happen, and I want to make sure everyone that tried it got it working. Yes?
It doesn't play, like I had to type one print because it didn't do it automatically, like I think you said it would.
Well, sometimes you just don't write the one. Maybe you don't have, there's like a setting in here somewhere. Tools, settings, editor. I don't know, there's probably something somewhere about line numbers. There might be a setting to turn on. Did everyone have line numbers by default? No? Well, there's a setting somewhere. I don't know where it's hiding now.
Yeah, I got it.
You got it?
Okay, we're good.
Editor? I feel like it should be here, right? Oh, show line numbers there. So I have that turned on. You don't need to turn it on. I just like the line numbers, so I could say something like, you'll see on line 5, right? But you don't have to have them. So if you run it without the 1 in front of it, though, does it work? Yeah? Okay, cool. All right, there. Anyone else? Gotten into something sticky with it? All right. To the next topic. Okay. Print, values, variables, and types. Well, we already used print. Technically, we're already playing around with values. But this topic is going to cover a lot of the foundational, like really foundational stuff. Some of you that have experience with programming, you might be familiar with it, but you might not really be familiar with it with the detail that I'm going to get into. Maybe you are, I don't know. So, I mean, I put this as an activity. We're not actually going to do it, but I want you to take a moment. I'll give you 30 seconds to think about this to yourself. Like, these are all words you've heard before. Computation, computer, programming. These are all things you've heard before. But do you know what does computation mean? What does that actually mean? You've all heard that word, but what does it mean? Do you actually know what it means? It's kind of a funny question. And, you know, the idea of a computer is a lot more broad than just those things sitting on your desks right now, or your phones, or anything. Really, a lot of different things can be, by definition, a computer. Things like, well, your brain is a computer. And I'm not saying that as technically, I mean, no, by definition, your brain is a computer. It is. It just works a heck of a lot differently than these things. These are only one type of computer. People can build physical computers that don't work anywhere near the same way that those things work too. This is just one design of a computer. Something as simple as a lock, like a safe lock, is a computer. It takes input, it can produce some form of output, like side effect. It has different states. It's a computer. It's a very simple one, but it is. It's not nearly as sophisticated as something like this or your brain, but it is. So what is a program or algorithm? Sometimes these words can be used a little they'll be interchanged a little bit. But here I'll give you like 3 minutes. Talk amongst yourselves and explain to the people next to you how you made breakfast this morning, or if you didn't make breakfast, how one would make breakfast in the morning. Just go for it. Do it. All right. So what you just did was you explained a series of steps one would take that if they did, they'd have breakfast at the end, right? That's an algorithm. If I give you a recipe to make a cake, that's an algorithm. If I give you directions on how to get from point A to point B, that's an algorithm. All it is a series of instructions, a series of steps you would take to achieve something. That's it. Doesn't necessarily have to do with anything overly technical like computers. An algorithm is just these steps of things. So, who wants to give an example of what their program was, their algorithm was, how they made breakfast? Someone's got to do it. Yeah.
Crack to get 3 eggs.
You crack. Well, hold on a minute. Where are the eggs?
You want like some detail?
Well, I mean.
So I can go into the fridge.
Okay, wait. Where's the fridge?
Fridge would be the left side of the kitchen.
Left side. Okay, so you go to the fridge.
Grab the egg carton.
Well, you have to open the fridge.
So I open the fridge.
Yeah.
I reach down to the bottom shelf.
All right.
I grab the egg carton.
Yeah.
Bring it over beside the stove on the right side of the kitchen.
Yeah.
Bring out a pan from below.
Well, you left the fridge open.
Well, that's when I go back.
You got to go back to the fridge. Oh, sorry.
I put the pan on that stove. Turn on the element.
Mm-hmm.
You get some butter from the fridge in the pan.
How'd you get the butter in the pan?
Oh, a little knife.
All right. I'm being mean to you. Because what I was doing there too was kind of, if I tell someone to cook spaghetti, I could tell another human, all right, just boil some water, add some pasta and wait 10 minutes, whatever. And then there, I'll add salt to the water. You're done, that's it. And another human would understand. But the way I just communicated to you is at a very high level of something that we call abstraction. It's very high level. And we as humans like to operate at a certain level of abstraction, right? It's kind of nasty of me to be like, where'd you get the eggs? You left the fridge door open, right? Because, well, of course, like any human would understand the basics of that. You don't have to go into those details. But you could go into those details. You could break those abstract ideas of grab some eggs, put them in a pan, turn on the element, right? Like we could add more detail. It all is a bit of a matter of what level of abstraction do we want to worry about. I mean, I could be really nasty, be like, release arm, move arm forward, grab, like that would be ridiculous. But we could do that. Or I could say things like, contract muscles, this amount, and what, no, obviously we don't operate at that level of abstraction. But we could describe these things at this level of abstraction. That said, we don't like to get that low level if we don't have to, right? Because it's a lot easier to just tell someone to boil water, add salt, and add pasta, wait 10 minutes. All right, what is debugging? Well, debugging is most of what programming is. Debugging is trying to find the bugs or errors in your code. Sometimes errors are simple, for lack of a better term, and sometimes they're really sneaky and they'll only jump up every once in a while. But most of the time you're going to be wrong when you write code. And you're going to be wrong every single time you try to do something before you're right. So you're going to be wrong a lot more than you're going to be right. So just get used to that. Expect that to happen. Don't let that frustrate you. That's the process. Has anyone, in class, has anyone hit any Python errors? I know you would have when you were trying to run it. Do you remember what it said when you tried to hit run? Yeah. All right, but just right now, though, when you tried like the one, you had to add the one, what did it say? Do you remember? Probably said something like syntax error or... Try it again? Syntax error. That is a bug. There's something, now in syntax error, what that means is Python's trying to read what you wrote and it goes, not a thing. So a syntax error might be a simple bug, but what other, raise your hand if you've ever been programming before. I know I saw people in here that had programmed before, and you came across a bug. Raise your hand if you programmed before, really high, I want to see. Lower your hand if you've never found a bug. If you lowered your hand, you're lying. Programming is debugging. That's the process. You're going to be wrong every time before you're right. And we can talk about languages too. Right now, if it's not obvious, I'm going over some very high-level things before we start talking about some of the fundamental things we're going to get to. Languages. Python is a programming language. There's a whole bunch of them. There's a lot of really popular ones too, like your Java, your C, your C++, your C#. There's a lot. There's Go, Rust. The list goes on. There's a lot of programming languages. But for those of you that have spent time programming before, and for those of you that haven't, as we go in the course, it's going to be obvious to you that although when reading the programming language, sure it's English-y, right? You can understand what it's doing if you spend time doing it, but it's obviously not as, it's not like English, though, right? It's very different. English is a natural language. That's the language that I'm using right now, right? It's working, it's really broad in terms of what you can do with it, what you can express with it. But a language like Python is a formal language, and it has a very strict set of rules. In English, there's a lot of ambiguity, and sometimes that could be what you want. But you ever, turn left, right, wait, right or turn right? No, correct. Stuff like that's kind of funny. That happens with English all the time. If something like that happened in a programming language where there was ambiguity, you're going to run into trouble. Because, well, the program, or the computer wants to do exactly what you tell it, and if there's ambiguity, we've got an issue. So in things like in formal languages, we can't have ambiguity like that. And it's really bad for formal languages. But what's really kind of interesting is, and this is remarkably interesting, but we won't really get into why this is so interesting in this course. But a sentence like, this statement is false, I say to you, and you're like, okay, I guess it's kind of funny, right? This statement is false. Well, that's a funny statement because if I read that and take the statement at face value, if the statement's false, if I read this statement is false, that means I shouldn't trust what it's telling me, right? So, if the statement's false, if it's wrong, and it's saying this statement is false, that means I should assume it's true. Because it told me it's false, so I can't believe it, and because it's saying it's false, therefore, it must be true. But if it's, hold on a second, if it's true, then it's telling me it's false. But if it's telling me it's false, how, do we see the trouble here? We've kind of created a little bit of a paradox, right? This statement is false. Here's another example. What would happen to Pinocchio? You know Pinocchio, if he lies, his nose grows, right? What would happen to Pinocchio if he said to you, my nose is going to grow right now? What would happen? If he said, my nose is going to grow, and it didn't grow, that means he was lying, right? But what happens when Pinocchio lies? It grows. So if he says, let's flip it. If he says, my nose is going to grow now, and it does grow, well, his nose only grows when he's lying. So that means when he said, my nose is going to grow now, it means, well, he must have therefore been lying, which means that his nose wasn't going to grow, but it just totally did, which is how I knew he was lying. Pinocchio should never say that statement. It's a recipe for disaster for him. We've got a bit of like a paradox there, right? Raise your hand if that makes total sense to you in the sense of like wrapping your head around what the issue is. Raise your hand if you're like, yeah, what? I have no idea. Be honest. Okay, everyone understands. All right, sure. I believe you. It is a funny thing, but something like that to a computer is not okay. Because we've created like this paradox. It would go into like an infinite loop. This statement is false. That means it must be true. And if it's true, that means that I should listen to what it's saying, and it's saying it's false. And because it's false, and it says it's false, that means I should assume it's true. And if it's true, then it tells me that it's false. And so on, and so on, and so on, and so on, and so on. We've got an issue. But if I say that to you in English, you're like, oh, huh, all right. Right? It's not really an issue. You just kind of appreciate the funniness of that sentence. Okay, throughout the course, we're going to use some terminology. Not really, a lot of what I'm about to show you here is terminology I won't really be using in the course. But in the context of learning computer science, these are some important ideas here. You may have heard of a lot of them. Hardware versus software. This one's easy. Hardware is like your physical stuff, like your laptop, your keyboard, your screen. And the software is like the programs, right? What else do I have there? Input, output. Input is a way to input information. And output is a way to output information. Like input, keyboard, right? I can put information in. Monitor, like your screen, it puts information out. What else do I have? Processors, well that's like the thing that does all the work in your computer. It's the thing doing all the number crunching. Storage, things like your hard disk or solid state drive. This is where you have long-term storage on your computer. Then you have memory, it's like random access memory, RAM. That's not, it's kind of like the big storage, the hard drive or solid state, except that's storage that's like kept in the pantry, where RAM is storage that you've got on your countertop, like when you're making some food. It's stuff that you're like actively using, and then when you're done, you go put it back in like the long-term storage type thing. So your hard drive is like your pantry, and RAM is your countertop. Binary, raise your hand if you know what binary is. All right, so humans like to use a base 10 number system. We have 10 fingers, it's perfect for us, right? There's 10. And we have the symbols 0 through 9. There's a total of 10 symbols, right? In binary, we only have 2 symbols, 0, 1. And that's it. But anything you do with decimal, like with the base 10, like your addition, your subtraction, anything you do with decimal, you can do in binary. And the reason we like binary for computers is because, you know, like I know you've all heard like, oh, computers, it's all zeros and ones, right? Well, that's actually wrong. It's actually low voltages and high voltages. There's no zeros or ones running through the computer. It's low voltages and high voltages manipulating little transistors on your computer. That's it. So we like binary because, well, low voltage, 0, high voltage, 1. There. It's really easy for us mechanically for the computers. Compiling, this is a word that we would use if we were using Python. You don't compile, you could, but when you write a program, it's like in Englishy, right? I wrote print hello world. But if I give that to a computer just as is, the computer's going to go, what's this? I don't know what that means. So it turns that thing from the programming languages, it's like that print hello world, into something the processor would be happy with. The set of zeros and ones, that means the low voltages and high voltages. That's what the computer wants. So you would compile your code into that. And then there's something called like an interpreter, which is what Python uses. You don't compile the code, you just run it in an interpreter. Details that don't matter really for the content of this course. We could talk about them later if people get really interested. But old school programming languages, when you wrote code, it would get compiled to run on your processor. A lot of modern languages don't do that. They have kind of like a fake computer running on your processor. So you've kind of got like a program running that pretends to be a computer, and then the code you write runs on that fake computer. And there's some interesting reasons why we do that. None of those details, though, are important for intro computer science. Just a little FYI. Any questions so far? Now we're going to get back to actual code again, which is more fun. No questions or anything? Okay. All right. Well, we already used print. And just to make sure you're even more familiar, open up Colab again and print out something else. Print out whatever you want. I don't care. Put another message in there, whatever. And hit run and make sure it works properly, as you would expect. And if it doesn't, try to fix it. And if you can't get it working, though, take note of it because I want to talk about it, see if we can find what the issue is. So I'll give you a minute just to do this one. All right, who got another message working? Who will if they have 5 more seconds? Who here tried, but it didn't work? Something weird happened. No, everyone had it working? Oh, that's too bad. All right, well, print is what we call a function. You're all aware of functions. Presumably, you all had to take like at least grade 12 math? I don't know. Maybe you didn't. 11 math? I don't know. When is math not required anymore in high school?
After pre-calc 12.
What is that? Grade 11?
12.
Grade 12? There you go. So you all took that, right? And so I know you're familiar with functions, right? F of x equals blah, 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 blah. That's a function. Print a function. It's the same idea here. The function has a name, print. And then the function takes parameters. In this case, the parameter is what I put between the parentheses. And then what did that function do? Well, it printed that out to the screen. In math, you write like f of x. F is the name of that function. Not a very clever name, but f is the name of the function. And x is like the parameter. You're going to be writing print a lot. Get used to it. But here's another thing that's cool about print. Take a moment and appreciate what print is actually doing. You know, if I want to print something in the screen, I can just tell Python, print hello world, and then it does. I hit run and it works. But you know, there's a lot going on under the hood. This goes to that abstraction idea that I was being asked to do about. Because, well, think about what Python's got to do there, or the computer has to do. It's got to go, okay, so I need to print this out. So that means I need to find, okay, so that's the letter A. Now I need to know the shape of the letter A. Then I need to know which pixels on the screen I need to turn on to show the letter A. And there's a lot going on under the hood. Thank God I don't need to think about that though, right? Because I get to work with Python. Whenever I want to print something out, I get to work with it at the level of abstraction of just print this out. I don't need to work any lower level than that. It's fantastic. Thank goodness. So that's a nice level of abstraction there. It could be worse. Thank God it's not. Did that make sense? Any questions about what I was just saying? You know, when you get in a car, raise your hand if you drove here today. Not? Wow, okay. Raise your hand. For those of you that drove, keep your hand up. For those of you that drove, do you know exactly how your internal combustion engine works? Yeah, see? But thank God you don't need to, right? All I got to do is get in the car, turn the key, put it in drive, and go. I get to interact, I get to interface with my vehicle at the level of abstraction of that, as opposed to knowing about or all the bits and pieces of my car. Thank God I don't need to know that. Because we operate at a different level of abstraction. It's great. Our world is made up of levels of abstraction. You just never thought about it before, but computer scientists start to geek out about this stuff. Okay, values and types. And again, I'll just reiterate, if at this point you're thinking, man, this feels like a blitz of information, yeah, it kind of is. I just kind of want to get us up to speed. Everything I talked about before, the big thing to take away from that is really about like what an algorithm is and levels of abstraction and print. Now let's talk about values and types. Very common values that you will be using will have these types here. Strings, integers, floating point numbers, there's a bunch more. But when I said print hello world, I gave that print function the string hello world because I put it between quotes. Did anyone in here try to do it without the quotes? And it probably said like name error, I don't know what that means, right? Yeah, because you need the quotes. Let's see what happens if I actually get rid of the quotes. Syntax error, I guess. Oh, all right. See if I just do hello. I want to see if it gives me name error. Yeah, name error, whatever. So let's just work with hello here. I have to put it in quotes. That means that the value, hello, has the type string. It is a string. String is just like a string of characters to make a string. We saw strings, they can have spaces in them. Your strings can be as long as you want. This is just a one-word string. Now it's multi-word string, whatever. But everything's in between quotes, and everything between those quotes has, it's like, there's that value, and it has the type string. So if I said, quotes, A, B, C, D, E, F, G, there, I have the string A, B, C, D, E, F, G. Its value is A, B, C, D, E, F, G. Its type is string. Like letters and whatnot. I mean, you could have numbers in your string, but they're just the characters. They're just like the numbers in the string. But I could also do something like this. 1 plus 1. And run that, right? 1 plus 1. There's no quotes there. I'm going to get rid of this here. I wrote 1 plus 1, right? One plus one. I gave Python two numbers. There's no error, there's no quotes there. I just gave it two numbers. Well, I gave it a number, an operator, and a number. But I said 1 plus 1. So the value 1 there, one of those ones, let's get rid of the addition part. We can get rid of that. If I just say 1, there's no quotes around that 1. It prints out the 1. But there's no quotes there. So it has the value 1. But it is of type integer. It's a number. Its value is like it's a number. It's the number 1. Interestingly though, if I do this, what value is that? 1. But what type is it?
A string.
It's a string. How do you know? Well, the quotes. That tells you. That's the trick. Yes?
What's the difference if you use typing 1 plus 1 versus print 1 plus 1?
The 1 plus 1 is kind of cheap. But this is one thing I don't like about Colab. Colab will be nice and kind of show you the last value if there's a value floating around. So 1 plus 1 is 2. Python says that's 2, and it tries to give it to something, and there's nothing that gets it. Let me put it this way. If I say print 1 plus 1, print 2 plus, we will see 2, 4. Okay? If we get rid of the prints, though, and we run it, you'll only see the last one. So use prints. I was being bad by not using the prints, but 1 plus 1. It's just trying to be helpful, and it only shows you the last thing, though. So if I had a whole bunch of them, it would only ever show you the last, where if you want to make sure you're printing out everything, you just use prints. Good catch. And it's funny, that's something I hate about Google Colab. So, and here's another funny one, too. So, 1 is 1. 1 is the integer 1. So its value is like the number 1. But with the quotes, it's the string 1. And funnily enough, we can actually have 1.0. And that, like, what value is that? What value is that? It's not a trick question. 1. Why? Literally, it's 1. It says it right there. I know 1.0 means 1. But its type isn't an integer. Its type is, we call a floating point number. It's a fancy way of just saying it's got a decimal in it. So, numbers that have decimals and numbers that do not have decimals, they might have the same value, but their types can be different, which is weird. So the string 1, the integer 1, and the floating point number 1.0, they all look the same, but they actually are of different types. So all of the values we will ever use in any of our programs have a type. If this is throwing you off, you're probably thinking too hard, which is a common mistake. Actually, I want to take a moment to say this. A lot of times, when people start to struggle with the concepts as we go, chances are you're trying to connect some dots that don't exist. You're expecting it to be more complex than it is. You're thinking too hard. To be good at computer science, you gotta be dumb. I'm telling you. If you overthink it, you're making things harder for yourself. Now, when I was dealing with values like this, when I just wrote the number 1, we call this a literal. Don't be surprised if I never talk about literals again for the rest of the course, but just to be precise, this is called a literal. It's a 1. It's literally 1. Why is it 1? I just wrote 1, and 1 is 1. It's literally a 1. And here I talk about 1 is not the same as 1.0, which is not the same as the string 1. Now, in some programming languages, if you ever want to have a value in there, you need to actually tell the programming language, okay, here's the number 1, and it's an integer. Python tries to be clever, and when you say just 1, it'll be like, oh, that's the integer 1. If you write 1.0, it's going to say, okay, that's the floating point number 1. If you write quotes 1, it knows it's a string. But in some languages, they're not that smart. You got to be more explicit. So Python could be helpful, but sometimes that relaxedness can bite you a bit. Just be warned, but you'll be fine at this stage. Yeah, Python will guess. The upside is, less to worry about. Downside is this can cause errors in your code. And we'll talk a little bit more about trying to address these issues as we go through the course. So, we know about print. It's a function to just print stuff. And I'm going to show you another function. Here's the second function you're going to learn about, called type. And it'll actually tell you the type. Well, here, let's print out the type, so I'm nesting functions right now. Let's just do type for now. If I say type 1, it tells me it's an str. What do you think str means? String. If I say 1, int, what do you think that means? Integer. 1.0, float, floating point number. So type is another function, and that function takes some value, and all it does is tell you what type that value has. Now, in the examples I have in the course notes, I've nested the functions, so I said like print type, and this goes back to what you were talking about like how come when you didn't add the print it showed you? That was only because it was being nice. I prefer to do it this way where you explicitly say print. Point being is I'm saying print, let's think about it this way. This is a nested function. First thing it goes inside the parentheses, by the way, we're gonna hit this idea way harder in like 2 weeks or so. So don't panic, but I'll just explain it now anyways. I've nested the function. So what it's gonna do is it's gonna go, oh, there's the number 1. Oh, but there's a function around the number 1 saying the type of 1. Oh, what's the type of 1? 1.0, oh, it's a float. So now the function type 1 returned the value to me that says float. And then I said, okay, print that out. And then Python goes, oh, okay, it was float. That's all. Okay, and all of these things like print 12, well, that'll say int. Hello world, string, 3.75 float. Well, this one's a funny one. What happens if you take the type of the type? Well, it's a type. It's weird. Don't worry, that's a funny little thing. So we're using 2 functions so far, print and type. Questions? None. So everyone's okay. Man, lecturing gets boring if people don't ask questions. All right, do this real quick. I'll give you a minute to do it. Write a single line program to print out the integer 1. I already did it. Prints out the string 1. Can you tell the difference just by looking at the output? Do that. You can even write these 2 programs one after the other and run it all in one shot. So if you're following along in Colab, do that activity really quick. I'll only give you a minute because I'll do it as well. There, I did it. I just did them one after the other. So the first line of the program says print out the number 1, the integer 1, and then immediately after print out the letter, the string 1. And so the output, we've got 2 lines. The first line of the output corresponds to the first line, the first print, and then the second line is the second print. When you look at that 1 and the 1, can you tell the difference? You can. No, you can't. You know, if you look really close, technically, no, there's not. There's no difference. When you print it out, you can't tell the difference. So, when I was saying before, some programming languages make you really explicit about your types when you say this value, oh, it's an integer. This value, oh, it's a whatever. I'm imagining you can see this and be like, oh, you know, I can see this being a potential issue of confusion where I can't actually tell the difference. You know, I can look at the values, they both look like 1, but, you know, we know 1 was an int and 1 was a string. So when in doubt, you can use that print function, and then you would And, oh, that one's an int. There, 1, but that was an int, and then 1, and that's the string. So there is a way to find out. Any thoughts on that one? Yes?
Is there going to be a way where, let's say if we're writing a bunch of lines, we can go back to the bottom and be like print type of like line 3 or something like that?
Well, you wouldn't say line 3, but what you would do is what we're just about to talk about. I like where you're headed. So, literals are great. There's the number 1, literally the number 1, great. But they're not, they're fine and all, but we want to use something called variables. Something, a named something, that can store a value for later. So I can use it later. So, if we go with the example I have there, I say a equals 5. I ran the program a equals 5. Now, raise your hand if you love math really high. Okay, you're going to hate this. Equals, in most programming languages, at least the really, really popular ones, does not mean what you think it means. Equals in math is a statement of fact. If I say A equals B, that means that the value of A and B are equivalent. When you look at this and you're like, oh, A and 5 must be equal. Well, no. I mean, yeah, as a consequence of this line of code, but equals is an assignment operator. It means, okay, the literal 5, it's the number 5, great. Put it in A. So now, if I go print A, and I hit run, what do you think's going to happen? Everyone on the count of 3 yell it out. 1, 2, 3.
5.
Why? Well, because the value of A is 5. So this would be kind of what you were talking about. Like, oh, if I want to go back to line, well, you would say, okay, well, what's the type of the variable A? So that's how you would kind of answer that question. I like the way your head's in the right spot. That's good. So there we go. Now, what do you think's going to happen if I say this? Whoop. A plus 5. 10. It can't be that easy, can it? Well, it is. Because A has the value 5. Now, if I hit run, this is where it might trip you up. But the trick to this is your program runs one line at a time. So when I hit run, what do you think will be printed out? It's not the 10. The 10's from the previous run. 6. Why? Well, because the first line of code says, okay, great, make a variable called A and store in it the value 5. Cool. All right, now the variable A, store in it the value 6. The number 5 that was there before is gone. It's obliterated. We forget about it. So then on the third line, when I say print A, well, what value does A currently have? 6. That's it. So variables are great. So this is exactly what I just showed you. Print 5 and print A will give you the same thing because the literal 5 and the variable A have the same value, the integer 5. Okay, we'll end here.